Rational functions. That looks pretty irrational to me. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are putting one polynomial on top of another one and seeing what happens. Rational functions are the family of functions that are one polynomial divided by another polynomial. In the strictest sense, they look like this, which is a lot of notation, kind of like polynomials. But the thing to gather from this is one polynomial of degree n over another polynomial of degree m. The leading coefficient of the upper polynomial is a sub n, and the leading coefficient of the lower polynomial is b sub m. So it's not actually all that bad. Rational functions have a few key properties, 4 of them in fact, that I like to go through in order as I solve my rational function. Those 4 things are horizontal asymptotes or slant asymptotes, y-intercepts, vertical asymptotes and holes, and x-intercepts. Horizontal asymptotes are horizontal lines that the function never touches but always approaches as x approaches infinity. Slant asymptotes are functions that the function approaches as x approaches infinity. Now, it is possible for the function to cross the horizontal asymptote in the finite world, but as it approaches infinity, then it's always going to approach that horizontal line and never cross it. In order to find the horizontal asymptote for any given rational function, we're going to compare the degree of the numerator and the degree of the denominator. If n, the degree of the numerator, is less than m, the degree of the denominator, then the function is said to be bottom heavy, and therefore the horizontal asymptote is simply y is equal to 0. If n is equal to m, then the function is said to be balanced, and the horizontal asymptote is equivalent to the horizontal line y is equal to a sub n over b sub m, which is just the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. If n is greater than m, then the function is said to be top-heavy, and we get a slant asymptote. That slant asymptote is equivalent to the quotient of the numerator divided by the denominator. We can find that quotient by doing some long division and neglecting the remainder. That quotient is our slant asymptote. Y-intercepts. This one is nice and easy. All we need to do is plug in 0 wherever we see x. So the rational function will be equal to always the constant term in the numerator divided by the constant term in the denominator. Now, before we move on to finding vertical asymptotes and holes, as well as finding the x-intercepts, the first thing I do is factor both the numerator and the denominator of the rational function. I do this because I need to do that for both finding the vertical asymptotes and the x-intercepts, so I might as well do it right now. Now, in order to factor the numerator and the denominator, we need to factor those polynomials. And sometimes that's easy, sometimes it's a little bit difficult. But again, what we want to do, kind of like what we did in the polynomial episode, was to use long division to find the factorization of the numerator and the denominator. We can also use normal factoring if we have, say, a quadratic. We can use factoring by grouping, or we could even use synthetic division. The thing we just want to keep in mind is that we need to factor both the top and the bottom of this rational function into as small of factors as possible. Hopefully those are linear factors like x minus 1 or x minus 12, something like that, or they are non-factorable quadratic factors. So x squared plus 1 is non-factorable in the real number system. Once we have that factorization, we can move on to finding vertical asymptotes and holes. Remember that we can't divide by 0. That's an undefined value. So if the denominator of this rational function ever becomes 0, then we don't have a defined value for this function. That's where our vertical asymptotes will be. So to find our vertical asymptotes, we set the denominator equal to 0. We'll have one vertical asymptote for every unique factor of the denominator. Wait, but what about wholes? Wholes are where a factor in the numerator cancels with a factor in the denominator, so that where we would normally have a vertical asymptote, we actually get a hole in the function. Instead of an infinite discontinuity, a vertical asymptote, we get a removable discontinuity, which is a hole. Take this rational function as an example, x minus 1 over x plus 2 times x minus 1. Normally we'd have a vertical asymptote at x is equal to -2 and x is equal to 1. But because that x minus 1 factor cancels out in both the numerator and the denominator, we actually have a hole at x is equal to 1 instead of a vertical asymptote. And so this function actually looks just like the rational function 1 over x plus 2, except it has a hole at x is equal to 1. Finally, our x-intercepts. Our x-intercepts, like normal, are wherever the function is equal to 0. So we set y is equal to 0. Fortunately, there's no way for the denominator to affect the rational function such that it will make the whole function 0. So we can neglect the denominator when finding our x-intercepts. So all we do to find our x-intercepts is to set the numerator equal to 0. And since we've already factored our numerator, all of those zeros are just going to fall out of that factorization. So simply set the numerator equal to 0 and solve. And that's most of what you need to know about rational functions. The last thing I want to bring up is this, comparing rational functions to power functions, where p is less than 0. Remember from our power functions episode that if p is negative and even, it has even symmetry across the y-axis. And if p is negative and odd, it has odd symmetry across the origin. The same thing goes here, except we're going to look at individual factors of my denominator to talk about those vertical asymptotes. So for instance, if I have this function 1 over x minus 1 times x plus 2 squared. From x minus 1, I get a vertical asymptote at 1. And because the power above x minus 1 is just 1, which is odd, the symmetry of this rational function across that vertical asymptote boundary is going to be an odd symmetry. And now if I look at this factor, x plus 2, that gives me a vertical asymptote at x is equal to -2. But because that factor has a squared power associated with it, it's actually going to exhibit even symmetry across that boundary, x is equal to -2. So by using what we know about power functions, we can predict what a rational function with these various powers in its denominator is going to look like. In the next episode, we'll take a look at an example, but in the meantime, why don't you try it out yourself? We're going to try to graph this rational function here, labeling all important points and asymptotes. Have a try yourself, and I'll see you in the solution.